Who has kids here? Who has kids? Y'all have a smartphone strapped to your ass, and it's got an ARM processor in it. What was the first platform ARM was built for?
Acorn.
Sir. This is the alt control hack threat modeling card game.
Hey, what was the answer?
Acorn.
Acorn, the BBC microcomputer. One more, Duck. Oh, shit, I suck at baseball. Are we good? AV? Are we good back there? Okay. Robert Graham is going to talk to us about defending the internet at scale. What a scale. Have a good one.
So good morning. What my talk today about is scale. And whenever we talk about scale, we often use the word instead performance. And there's actually a very difference between performance and scale. What this graph shows is the typical Apache problem. Apache, the more connections you establish with an Apache server, the worse the performance goes. So if you've got an Apache server that has very short PHP transactions, if you're going at 1,000 connections per second or HTTP hits per second, at any point in time, the connections only last a couple seconds. So you're only going to have a couple thousand established connections with the server at any point in time. But let's say you convert that server to something that does long-term downloads, where connections last 10 seconds or 20 seconds. Now if you're doing 1,000 connections per second and you've got 10-second long transactions, you're going to have 10,000 connections open. And in terms of performance, this shouldn't make a difference how many connections are established. It should be the same number of bytes per second or requests per second that you handle. But in fact, Apache's performance, it drops off a cliff. It basically fails. So, and this is something that hackers have used for almost 2 decades now, just establish a lot of connections with the server, and then the server goes down. That's what happened like in the Aaron Schwartz case, where he just did a lot of downloads and had a lot of simultaneous downloads, and Apache couldn't handle it and it fell over. So let's say I've got an Apache server, it's handling 5,000 connections just fine, but I want it to handle 10,000 connections. What do I do? Well, maybe I'll just upgrade my server to twice as fast or twice as many CPU cores. Because if I'm handling 5,000, doubling the speed should give me 10,000. But this is in fact what happens, is I don't get double the scale. I get double the performance, so the performance goes up, but the scale only goes out a little bit. I'm only getting 6,000 connections for doubling the speed. The same thing happens if I double it again to 4 times as fast, or 8 times as fast, or 16 times as fast. I'm 16 times as fast, the performance is off the graph. It's way more than I need. But yet I still haven't solved my problem of handling 10,000 connections. So the idea I'm trying to communicate here is the idea that maybe there's a different solution to the problem. That instead of trying to increase the performance of the software, change the software so it doesn't have that performance graph. Change the graph. So, and that's what people have done. There's some new servers out there like NodeJS or Nginx that are becoming more and more popular web servers instead of Apache. And this line shows their scale. Is whatever performance they have doesn't change that much depending upon the number of connections. In fact, the servers may be quite a bit slower. So I might be running that server, an Nginx server on my laptop, and so it's going to be a lot slower than a high-end server running Apache. But yet, as I do scale, their performance, the Nginx performance, doesn't drop off the graph as fast. So at 10,000 connections, the laptop is actually faster than even a 16-core server. So that goes back to my original point about performance versus scalability. These are our orthogonal concepts. Performance is one direction, scalability is the other. So if you remember one thing from the presentation is that scalability and performance are these orthogonal things, and they don't mean the same thing. If you're talking about scalability, you shouldn't be using the word performance. So who this talk is for? For the most part, it's for coders. It's for how do I develop software myself to make it scale? Or I've got a problem with my software, it's not scaling, what do I need to do to change it? It's also for everyone else. We have this idea, we're managing our networks, and this idea of what our hardware is capable of. And there's a lot of rule of thumbs that are false. With all of our experiences with Apache, we tend to think, well, inherently a server can only handle a certain number of connections. But in fact, it can handle a lot more because it's Apache's problem, it's not the hardware. So when we buy hardware, spec for hardware, we need to know what the performance capabilities actually are. So this talk is not about Apache. Apache is the problem that was worked on 10 years ago in a project called C10K. This was back when they said, hey, look, Apache fails at 1,000 connections. What do we need to do to make things scale? And that's the C10K problem. Let's do what we need to do to reach 10,000 concurrent connections. This talk is the next sort of level. I call it C10M just to reflect the old problem. And that is how we get scalability in the future with things like IPv6 and as the internet grows. The problem I'm going to talk about for scalability is the kernel. So I'm going to talk a little bit about the Unix kernel and where a lot of today's scalability problems come from. I'm also going to talk about the primary solution that C10K came up with, which was using asynchronous programming. But those really aren't the focus of my talk. My focus of the talk are the next 3 points of the scalability problems that come with handling packets, scalability problems that handle with massively multi-core servers, and the scalability issues with memory. Then we'll get to a little question and answer session. So actually, I had 6 sections of my presentation. It was like 150 slides, and I realized I couldn't cover it. And it's like 2.5-hour presentation. So in the slide deck, there's 3 other sections here that when we post the slide deck to the web, you'll have these other sections, but I'm not going to cover them in the talk. So let's talk about history. So back when we had clay tablets, we had Apache. And the way Apache worked was we'd use a CGI interface, would spawn a process and handle your connection and kill the process. And that didn't work, and so people came up with this idea of what do we need to do to change things to reach 10,000 concurrent connections. And there were 2 basic problems, and both of them, to start with, were in the Unix kernel. The first one was with threads, or processes. We launched a process to handle each TCP connection, so 10,000 connections meant 10,000 processes, or 10,000 threads. And what would happen is that every time a packet arrived, it would walk down that list of all 10,000 processes in the kernel to figure out which thread needs to handle that packet. So the more connections you had, the longer the list it had to traverse. And this is sort of a classic order of n squared problem. Whereas n is actually number of packets or level of traffic times the number of concurrent connections. The other problem was, well, we know how to do web servers, and I'll mention that later, without using a thread per connection. We can actually just have a socket per connection and use the select call. Select is a function call in Unix, or the poll function call. But we had the same scalability problem, is it would walk, when you give it a list of sockets, of 10,000 sockets, representing 10,000 connections, it would walk the entire list. So the longer that list got, performance would drop off the chart. And in both these cases, whichever way you designed your server, you would still have that graph of performance dropping off a cliff. So the first solution was to fix the operating system kernel. You change the thread scheduling, and Linux did a lot of work with this, so that it's constant time. That it takes the same amount of time to switch from one thread to the next, regardless of the number of threads in the system. The other one was to come up with a new function call, or a new API, called epoll. Epoll works like the traditional poll in sockets programming, but it's now scalable. It takes a constant amount of time to switch from one socket to the next, reading packets, without having to walk that entire list. But the real problem is even though they fixed the thread scheduling, it still didn't work with threads. You really had to go with just polling off the sockets. And this is a technique known as asynchronous programming, or event-driven programming. And there's a lot of web servers now that use this, like NodeJS, Nginx. Nginx, by the way, is spelled Nginx, and Light HTTPD. So when you go to these massively scalable systems like Twitter's front end or YouTube or Google, it's using these scalable servers and not Apache. Oftentimes they're just caches in front of Apache, but the front end has to be something scalable. So the solution of C10K, it's taken a decade really of moving away from Apache to scalable servers. And in the last couple of years, we've seen a faster and faster transition from the old Apache non-scalable model to scalable servers. And so this is a graph from Netcraft of the million most busiest sites, where Apache still dominates, unfortunately. But we're seeing the rise of, in this case, Nginx, but not just Nginx, but the other scalable web servers as well in the other category. But that's the past. That was a decade ago when we had Apache, realized it didn't scale, and now we're moving away from it. What this presentation is mostly about the future. Future internet growth or internet scale. When IPv6 comes along, that means a single home user can establish easily 10 million connections with your server. Right now, a home user can only establish 65536 connections for the number of ports that you can have with one IP address going to your server. With IPv6, they have as many IP addresses as they want pretty much, and every server on the internet now is going to have a huge flood just from one desktop taking down scalability. So we need to go to the next level of scalability. So I'm going to define what I mean by C10M. The first thing is 10 million, from what the name is 10 million concurrent connections. That's what from C10K is 10,000 connections. Now it's 10 million connections. But more than that, there are a bunch of other scalability metrics, one of which is the number of connections per second, the number of HTTP requests per second. And for 10 million connections, you need to be able to sustain a rate of about 1 million connections or requests per second. That means that every one of those connections can last about 10 seconds. And what I'm talking about is 10 gigabit Ethernet. So it's on servers that have 10 gig connections to the internet. I'm talking about 10 million packets per second. Scalable servers now you expect to have maybe 50,000 packets per second performance. This is going to a much higher level. In the past, this used to be a big scalability issue because servers could only handle maybe 100,000 interrupts per second, and every packet caused an interrupt. And so therefore, at 100,000 packets per second, they just fall over and die and do nothing. Another issue is latency. Scalable servers may be able to handle the performance, but the latency might shoot through the roof. And we see this a lot with voice over IP applications, where it's handling, in theory, the bits per second, but latency is several seconds long, so you can't talk on the phone. A related issue is the maximum latency, known as jitter. So if every so often, if most packets have low latency, but every so often one packet has a high latency, like once a second, you'll notice that talking down the phone. So you have to keep latency low. And at the same time, our solution to this problem needs to be scalable across many, many cores. Right now, software scales typically to about 4 cores, which is why phones and mobile devices don't really have anything more. But servers scale easily at 10-core, 16-core servers, and so we need to redesign software to accommodate that. So who needs to scale? So in my experience, my code was IDS, IPS, that needed to handle internet scale because we connected up to a server backbone and had to monitor all that. But there's so many other applications out there that need this sort of scale. Like the first one on my list is a DNS root server. That needs to be able to handle 10 million incoming DNS requests per second, look them up in this table and respond. Or Tor exit nodes, or let's say I want to nmap the entire internet and I want to be able to have it complete in a reasonable amount of time. So I can go down this list of all these different applications that need this level of scale that I can't simply solve by throwing more servers at it. So who does the internet scale today? So the purpose of this presentation comes from the fact that people are doing this today, but it's not really in the open source community. I can't go into GitHub and download an application that gives me my Tor exit node at 10 million connection scalability with 10 million packets per second. And the reason is that the people who are doing this are doing it, they're not selling you the code, they're selling you the appliance. The scalability issues are so delicate that they don't really want to sell you the software that runs on hardware. They're going to send you everything pre-configured that is known to have a certain level of performance. So you're buying these devices today already and sticking them in your data center. If you pull off the cover of a lot of these devices, what you'll find inside is an Intel motherboard with an Intel processor. It's just that you can't get to the software to see how they're doing it. A lot of these devices, though, aren't x86. They're not Intel processors. They're something called network processors. And network processors really are just our traditional RISC processors. They're based on Spark, PowerPC, or MIPS. And the only real difference that they have is they have some fixed function units for doing compression or encryption, but fundamentally, the devices we're buying for high-performance networks, inside the boxes is just software running on hardware, on your traditional CPUs. So if you wanted to build, if you got a VI and GCC and you want to go build a really scalable application to 10 million connections, what sort of hardware do you need? And the answer is, it's pretty much just a desktop computer, not even a really high-end server. My software is scaling to this level, and it runs on something that's basically a $5,000 computer with a dual socket system with 8 cores with hyper-threaded. So that's what the capability of hardware is. So if you take away something from this talk is that if I really need scalability, and I've got my servers here, and my engineers are saying, well, servers can't do more than 10,000 connections, you need to know that, well, yes, they can. It's because you've made a bad choice with the software, for example, choosing Apache, and that's your problem. It's not the underlying hardware that's your issue. Hardware, I can go off to Newegg right now, buy hardware for $5,000 that easily scales to 10 million connections. So I had 3 sections in my talk, and all 3 have a common theme to them. How do I solve scalability? And the problem really isn't scalability, but how we do it today. How many people have recognized this book? So most of the audience, or half the audience. This is the most common textbook in college for learning network programming by a guy named Richard Stevens. And it's sort of a holy book, because when we were in college and we were kids, when we learned network programming, we had these epiphanies of like, wow, byte order, this is like, it blows my mind. I never thought about that before. And so we look back fondly on our experience with Richard Stevens' book. But unfortunately, it teaches us a lot of bad habits, because what the book is about is not network programming, but about Unix. And that kind of is reflected in the title with Unix in big letters. And that's our problem is if we were doing pure scalability programming, pure network programming, we actually wouldn't interact as much with the Unix kernel. So the problem with the Stevens book is telling us the way to do network programming is through Unix. Have Unix do all the heavy lifting for you, and you just write a small little server based on top of Unix. But the kernel doesn't scale. And that's what my 3 points are really about, is the problem with scalability in the kernel. And the solution is to move outside the kernel and do everything yourself, do all the heavy lifting yourself. So my talk is about network programming, not Unix network programming. So one example I want to describe is something known as byte order. How do we represent an IP address? And there's 3 canonical forms. So if you go into any programming language, whether it's Java, JavaScript, Ruby, Python, there's only 3 ways we represent an IP address. One is as a string of just 10.1.2.3. One is a sequence of bytes. And the third is as an integer, as a 32-bit integer, because IP addresses are 32 bits. But in Unix, they chose a 4th format that's not one of these 3. And this 4th format only happens in the C programming language. And that is where they cast some bytes. I have 4 bytes. I'm going to cast that as an integer and represent that as an integer. Now on Spark RISC CPUs with their big endian format, the variable IP4 is the same as IP3. They represent the same value. But on Intel processors, it's a different value. They swap the bytes. So what happens is there's an unending confusion on when people write code between what Unix wants as a byte order and the three canonical correct forms. And this confusion is something that people, the order of bytes is sort of like the simplest concept possible, but one we kind of avoid thinking about, and it leads to endless bugs in code. There's also the problem that on RISC processors, this crashes. When I dereference 4 bytes and it's on an unaligned boundary, the processor will crash, or the process will crash. So, and this was a solution that they came up with in Unix programming, is we'll have this function that'll take care of the problem for you. So here's if you run the code, and here if you run the output, here's the difference between IP3 and IP4, and you can see if the bytes are swapped. The lesson here is that these functions that you learned in your Stevens books, like H2NS, to solve the byte order problem, it wasn't a problem. If they'd done it correctly, there never would have been a problem. You never would have had to deal with byte order. When you program in JavaScript or Java or Ruby, and that's your first programming language, you don't even know what I'm talking about, because those languages always did it correctly. So the solution, that epiphany you had in college about, wow, byte order, it wasn't an epiphany. It wasn't a problem. It was only a problem because Unix made it a problem, and then Unix gave you the solution that really triggered your imagination. Wow, Unix is cool because it solves problems like this. So, as I mentioned before, the solution that Nginx has over Apache, and why Nginx scales, or NodeJS scales, is because they're asynchronous. And what synchronous is Apache launches a thread for every connection. That means every time a packet comes in, the kernel needs to decide, well, which thread does that packet go to? And so you're using the thread scheduling system as a packet scheduling system, and that just doesn't work, and things don't scale. And so what Nginx does is say, okay, the operating system is doing it wrong. Using the thread scheduler for packet scheduling is just wrong. So I'm going to get away from that. I'm going to do the packet scheduling myself. I have a sockets and a list of sockets. Find out which one has data ready for them, because packets have arrived. I'll then read only on that socket, and the function won't block because it'll return immediately because there is data, and I'll process it. So the moral of the story of asynchronous is that Apache let Unix do the heavy lifting. That was the wrong solution. With Nginx, NodeJS, or light HTTPD, those programs do the heavy lifting themselves. So let's talk about packet scaling. The problem with packets is that they go through the kernel. And this diagram here is a diagram of what happens in the Linux kernel. And you see all these lines going everywhere, accomplishing everything. You got the threads going on, you got packets going on, it's going through multiple layers. And so the network stack is sort of my focus here, and in particular, the tortuous route that packets take to go through the stack. So when the packet arrives, it goes through layer after layer after layer after layer, and finally gets to your application. So the idea is we don't want to let the kernel do the heavy lifting. That instead of going through the kernel with the packets, we sort of bypass this whole step. And the way we do that is we write our own custom driver. That instead of a network driver that shows up with ifconfig, I'm going to write my own network driver, my own driver for the hardware. And the operating system might not even see it as a network driver. It might be device XYZ driver, and it doesn't know what it is. And all that driver does is instead of sending the packets to the kernel, to the TCP/IP stack, it just sends them directly around to my application. And so there are three main, if you want to do this yourself, there's three main sources. Well, actually four. One of which is you write your own driver from scratch, so that's really painful. But there are three sources of drivers you can get to do this for you. One of which is an open source for Linux called pfring. So if you have Snort or something and you want it to be faster, you've probably gone to pfring to get a better driver. In FreeBSD, they have this NetMap project. It's not quite as fast and uses the kernel more, but bypasses large sections of the kernel. And it does a pretty good job. And then Intel has a closed source driver that you can license. And the advantage of the Intel driver is that it's closed source, but there's a lot of companies out there that have products for it. So with PF Ring, that's great for sniffing applications or for lightweight stacks. Let's say I want to use PF Ring to do 10 million DNS requests per second on a root DNS server. And that'll work just fine, but that's because I don't have TCP. If I want TCP IP, I sort of need a stack. And so there's several stacks available for the Intel driver that are custom stacks that will scale, whereas the Linux TCP IP stack won't. So how fast do these drivers work? So Intel has a benchmark where they're getting 80 million packets per second. This is 80 million packets received and then retransmitted per second on a fairly lightweight server. And the thing about the Intel driver is that it's going through user mode. So it's shipping the packets all the way up to user mode, making a decision, and then retransmitting all the way back out again. And that takes, if you look at the processor, their benchmark was on an 8-core CPU, that's 2 gigahertz. So that comes out to 200 clock cycles per packet. Their benchmark is actually kind of unfair. They're benchmarking against the Linux bridge mode, which keeps all the packets in kernel already bypassing most of the kernel anyway. To get packets in Linux up to user mode, like receiving UDP and retransmitting UDP, Linux doesn't do more than 1 million packets per second. So the difference in performance is really 80 to 1 of using your custom driver that's bypassing the kernel versus going through the Linux kernel. The math here is in my C10M, I only propose 10 million packets per second. So if I'm getting only 200 clock cycles per packet, that leaves me about 1,400 clock cycles to do something useful, like if I'm running a DNS server or an IDS or a web server, I've got 1,400 clock cycles per packet. I mentioned this because we're going to do some math later on that. So with PF Ring, you get raw packets without a TCP stack, so you have to do your own TCP stack. And so people are increasingly, and there have been some numerous projects in the open source community where the people are doing user mode stacks. I don't know if any are production quality, but for the Intel DPK, there's a 6-win gate that has lots of people use it and get really scalable TCP performance. The concept here, Intel DPDK, what that stands for is Data Plane Development Kit. If you'll remember back in prehistory, back before in the clay tablet era, the way that telephones were switched is that people would take actual physical wires and connect you. So when you called someone, you got a direct electrical connection from your phone to their phone. And that was known as switching. And so you had the control system, which in this case were people plugging wires, and then the data plane, which was the wires themselves. So in the 1960s and early 1970s, the telephone switching system switched to digital, where you had, as the control system, a computer, and then the data system was some hardware that would just regenerate bits. So you had this concept of the computer's purpose in life was to control the network, not to actually transport the data. And that's where Unix came from. Unix was developed by AT&T to be a control system for their big, powerful hardware switches that would forward bits. And so that's the concept we want to think about. Is not that Unix was designed to be a server, it wasn't. Unix was designed to be a control system for other things serving the data. That we use Unix today as a server, as the data plane system, is sort of the problem that we have. And we shouldn't be really doing it. Unix wasn't designed for it, and it's about trade-offs. Is if I've got one application only on a system, I would design the kernel very differently than a kernel that does multiple applications. So that was packet processing. And the point is, with a data plane system, I can get 10 million packets per second. Going through the control planes part of a Unix kernel, I only get 1 million packets per second. The next thing I want to discuss is multi-core scalability. In the last 10 years, my first 3 gigahertz computer was, I think, 2001. My computer is still 3 gigahertz. So computers haven't gotten faster. What I have now on my desktop is a 6-core computer, hyper-threaded, so I've got basically 12 cores to work with. But the problem is that software doesn't scale like that. Most software scales to only about 4 cores, and even that 4th core is not much of an advantage over 3 cores. And what happens is that as we add more cores after 4, it's not that the sort of the performance levels off, the system actually will get slower and slower and slower as we add more cores. And that's because software today is written kind of bad. What we want is scalability that looks more like this. And what this is you'll notice that as we add cores, we get faster and faster performance. This graph actually has a curve to it if you look at it. Once we reach 16 cores, I'm only showing about maybe 11 times as fast. And that's bad. We really want better scalability than that, but still it's far better than the previous slide where after 4 cores, things got worse rather than better. So we want software that when we do our benchmarks, as we add cores, whether it's a DNS server, an IPS, a web server, a caching server, a Tor exit node, I go faster the more cores I add. So the thing about multi-core programming is it's not multi-threaded programming. When we learned code, we learned it with concepts from the Unix era, from the 1990s. Back then, we only had one CPU per computer for most all computers. The idea of multi-threaded software back then was that we had multiple different tasks all running on one CPU. It was multitasking. And when they needed to interact is when we learned how to do the multitasking or multi-threaded programming. But today, we have a very different system. We have an application, a network application we want to write to dedicate most of the box to one application. And our problem is how to spread that application across multi-cores. So instead of many tasks on one core, it's one task on many cores. And the problem, the scalability issue comes along with how we do synchronization. When 2 cores or 2 threads want to access the same data and manipulate it, one has to stop and wait for the other. Otherwise, if like one person reads 5, and they're going to increment it, one core reads 5 from the memory and increments it. The other core reads 5 from the memory and also increments it. So they both have the value 6, and then they both write the value back to memory, and we get 6 in memory, even though we incremented it twice, and it should be 7. So the synchronization we all learned in school, thread safety is really, really important. We had this epiphany like, oh my God, thread safety is a hard problem. I need to let the Unix kernel do it. And that's where we had features like mutexes or critical sections or semaphores, where I call a system call in Unix to say, hey, I've got 2 threads trying to access the same thing at the same time. If they conflict, I want you to stop one thread and let the other one continue. And that's a lot like the stoplight shown here in the picture, is when you have traffic in both directions, one side has to stop while the other goes. But what we need for scalability, and that's what you lead to the problem that around 4 cores in most software, most of the cores start waiting. And this transition in and out of the kernel starts eating up more performance than you're gaining. So what we need to design is an architecture that works like a freeway. When the crosswise traffic, both sides of the traffic get to continue all the time without ever stopping. And there's many ways of doing that, so I'm going to cover those ways. Consider the Linux kernel when you do the if-config. And what you see here is a picture from a Linux kernel where it counts the number of packets received, number of packets transmitted, and there's and drop packets, but those are all zeros in these counters. So I've got a multi-core kernel in Linux with trying to monitor the statistics in the traffic. And as I mentioned, if all the cores are starting to just add to the number of packets received, it'll corrupt the value occasionally and not count the number of packets correctly. So how does Linux do that? Well, in the past, what they would use is a semaphore. Is they would, when 2 drivers tried to update the same packets received counter, they would stop. So the idea was to you maintain multiple statistic counters. Every core maintains their own packet counts. Now another core, when you actually do if-config, goes through all those counters per core and adds them all together and gets a number. And this doesn't give you a corrupted value. It gives you always a correct value. So there's a number of data structures like this that require no synchronization. And you just have to change your problem a little bit. You don't need to synchronize. Another solution is called atomics. There are certain instructions in the CPU that you can access from, like C, where they're guaranteed to be atomic. So on x86, you have this lock prefix you put in front of an instruction like an add, and it's guaranteed to always never conflict. And it's expensive, so you don't want to do it for every transaction. It's like about 30 to 60 clock cycles, but it means both threads really proceed at the same time without conflicting. Now, the key word you want to Google after this presentation is something called lock-free, lock-free synchronization, where people have created whole data structures like hash tables and linked lists and stuff that thousands, and there's this Azure system, had 1,000 processors working in the same hash table. We can resize the hash table, you can insert and remove items at really, really high speeds by all threads that never have to stop and wait for each other. And it's really a cool thing. And so when you build your software, you don't necessarily want to do this yourself, you want to use the tools created by others. And you don't want to do it yourself because you should be afraid. And here's some terms you want to look for, like the ABA problem or the memory model problem, of why that it may look good to you what you're doing, but you really should look at what maybe an academic solution has where someone else has actually studied the problem and solved it. If you really want to get into lock-free programming, these are the sort of terms you want to Google and look at and see what the problem is and how you need to solve it. It's not just synchronization. Part of the problem with building scalable across cores is how do I write my threads? Do I have like each thread handle part of the problem, hand it off to the next? Like maybe one thread captures packets, one thread does the TCP stack, one thread does the application layer, another thread then generates the response. So each thread hands it off to the next. Well, that has a lot of synchronization overhead. The other threading model is a lot of worker threads, where each worker thread maybe pulls the packet off the queue and then runs through the whole stack, all the way from beginning to end, and then sends the response and gets the next packet. So all worker threads are doing the same thing, or threads doing different things handing off to each other. And there's pros and cons for each of these models. Finally, for multi-core scalability is you can configure the Unix kernel which core it's going to use. You can, on the boot parameter, you can say use the first 2 CPUs of an 8-core system, and don't use the remaining 6 CPUs, not yours. And then in your code, you use the function call of set infinity to set where your thread's going to run on one of those 6 CPUs that Linux isn't using. And you can also do the same thing with interrupts, so that your CPUs don't get interrupted. And what that means is that you own those CPUs and Linux doesn't, and it works great. So now I'm going to talk about CPU scalability. Memory scalability. The problem is that with these pictures are to scale. If I've got 20 gigabytes of memory, I only have maybe on a high-end server 20 megabytes of cache. And here's the difference in cache. So when I have a 10 million connection application with 2 kilobytes per connection, that doesn't fit in this cache. It doesn't even get close to the cache. That means every time a packet arrives for a random connection, none of the data associated with that packet is going to be anywhere near the cache. So every packet that comes in is non-cacheable. And this is not to scale, but kind of shows the problem. CPUs have cache for high-speed access to memory, but when it's not in the cache, it costs like 300 clock cycles to go out to main memory. And during those 300 clock cycles, it's just sort of sitting there twiddling its thumbs doing nothing. So let's talk about our budget. If I've got 1,400 clock cycles per packet, and that was back in the original Intel benchmarks, and it costs 300 clock cycles for a cache miss, that means I've got 4 cache misses per packet for my server, for my application. And so that's a problem. So in Linux, just the very basic optimal approach, path for the system is it goes to a hash pointer, it then goes to the TCP control block, then it goes to the socket entry, then it goes to the application layer data. And that's my 4 cache misses right there. Then I'm done. And so the strategy you have is when you think about this problem, well, how do I solve this problem? Well, instead of having a separate chunk of data for each of those issues, why don't I just co-locate them all together into one data structure? So allocate my TCP control block with enough space to also put my socket structure in there, and then enough space to put any application layer data. And instead of having a list of hash pointers that then point to the block, just pre-reserve that memory of one large, 10 gigabyte section of memory to hold pre-allocated all those blocks. So then my 4 cache misses are then reduced to 1 cache miss. One issue, so when we talk about memory, there's a lot of other issues that we have to deal with. For example, we know that Unix does paging. Like when I had virtual memory, page to disk, blah, 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 memory protection, how does it all work? Well, we sort of just ignore it because it doesn't really impact us. But when we talk about scalable software, it does. And the paging tables for 32 gigs, you're going to need 64 megabytes of paging tables. That doesn't fit in the cache, which means every memory access, the cache miss isn't one cache miss, it's one miss for the paging table plus one miss to what the paging table points to. And it's a detail that we can no longer just ignore. So we go through other strategies, like, okay, instead of just large data structures, if I've got a value that's only between 1 and 10, I need 4 bits to store. I don't need a full int. So I can go and compress my structures. Instead of like a binary search tree, like I've got a firewall rule set, I'm evaluating 10,000 firewall rules, instead of going through a binary prefix tree, maybe do another sort of tree, and this shows one of those things. They're called cache-efficient structures. So instead of using these ones, that a binary tree, even for 1 million entries, requires 20 references, 20 memory accesses. Well, a cache-efficient structure may only require 5 memory accesses, meaning 5 cache misses. One of the issues, if we've got a multi-socket server, one of the issues we can't ignore now is the fact that some of the memory is not my local socket, but across on the other socket, and it costs twice as much to go access it. Instead of using malloc to just sort of generically allocate memory, we have to start thinking of other structures for how I manage memory, like memory pools, like pre-allocate all my TCP connections all at once at the very system startup. And if I ever get a connection past that, I can't allocate memory. One issue with processors is they're multi-threaded. That the processor itself has its own idea of a thread. And Intel processors can run 2 threads per processors. Network processors or Spark processors can handle often 4 threads. And what that means is that when the processor stops, they can only actually execute one at a time, essentially. But when it must stop and wait for memory, the other thread can continue. And that sort of masks your memory accesses. And you should take that into account when doing your stuff. There's something called huge pages. And what huge pages are is it reduces that page table size. So it skips the last step of doing paging so that your application layer can handle large parts of memory and not have to go through the extra cache miss from the page table. But to make that really work well, you need to reserve that memory in Linux at the very start. So here I'm getting to the end of my presentation, and I want to take a look at what I've covered. And what I've covered is the fact that I've got some network adapters. If I go through the kernel, they don't really work all that well. I've got some CPUs, but if I use the traditional kernel mechanisms to coordinate my application, it doesn't work that well. Then I've got memory that I have to do some special stuff to make things work well. So the solution in my presentation is about is taking those 2 adapters away from Linux. And now I own those adapters. I put my own driver on them. They no longer appear in ifconfig. I do the same thing with CPU cores. At system startup, I use the max CPU setting. I give Linux the first 2 CPUs. I own the remaining of the CPUs. No interrupts will happen. Nothing will happen on those CPUs that I don't allow. I do the same with memory. At system startup, I tell it to allocate most of the memory for huge pages that will allocate in my application on startup. And so what I've gotten is, going back to that model, back with that picture of that switchboard, I've got the control plane, which is what I've left to Linux. It's in the blue part in this diagram. And then my code, all in the green part. And none of that code, after startup, none of it actually ever interacts with the Linux kernel. There's no thread scheduling, there's just no nothing, no system calls, no interrupts. And so, but at the same time, though, what I have, though, is I have source code. It's just code running on a Linux system. So I can debug it, I can run GCC. It's not some sort of weird hardware system that has weird hardware that I need custom engineering for. It's just my x86 system. It's just my normal code. So I get the performance of custom hardware that I expect from data plane, but with my familiar programming environment, development environment that I expect from learning Unix. So this is the last slide. So here are the 3 takeaways. The first is that original graph. Performance and scalability are orthogonal. They're not the same thing. Second is that these devices scale out much farther than the Apache, even farther than Nginx and NodeJS. These systems exist. It's just that there's not so much open source code there, so we can't put our fingers on them. And the third thing is you don't let the kernel do the heavy lifting. As I mentioned, it fails even at parsing, combining 2-byte numbers into one number. And it fails at scheduling your code. And the three things that I talked about were packets, the cores, and the memory. I put a lot more content in. I'm already at past my time just with having removed half the content. So I'm starting to put this up at this website, c10m.robertgraham.com. It's a little bit, this is sort of an outline there now. I'm going to post this presentation, other stuff there later on. So, thank you. So we have 10 minutes worth of questions.
You mentioned there were 4 ways to bypass the kernel, and I saw 3. Is the 4th Phil Woods version of libgcad or something else?
Oh, no, I meant write your own driver. Grab a card from some vendor and write your own driver for it. The Phil Woods thing was it bypasses part of the kernel. So in Linux, you have this idea of they call zero copy. And when they refer to that, they mean I've bypassed one traditional part of the kernel, but I've left like 5 other copies around. My technique was, not my technique, well, it was my technique, I wrote a driver for it, but the Intel DPDK or the PF ring is truly zero copy. It configures the network adapter to DMA directly into memory that's mapped into user space. And on Intel modern processors, the L3 cache sits between the DMA and memory. And what it says is, well, I'm not actually going to write to memory right now. I don't have to. And so and that's why Intel only has 200 clock cycles per packet. That's less than 1 memory access. Because it's never going to memory. The packet comes in, stays in the L3 cache, it handles it, and then retransmits it without ever touching memory. And so now that's zero copy. So Phil Woods was actually just removing 1 copy, and he called it zero copy, but copies went on. Question? So the question is are there any security concerns? And I'm going to wave. So I guess we're at time. So, and the answer is not really. So I'll be wandering out here while the next person's setting up, so you can come and grab me and tie me down and ask me questions. Thank you.